Dear student, you are welcome to our third class on heat and thermodynamics. Now we start with the topics of entropy. What is entropy? Entropy means disorder in a system. বিশৃঙ্খলা একটা সিস্টেমের বিশৃঙ্খলা, disorder of a system. Suppose you take some ice and water. Ice and water. Uh, then what is the state of the molecules of in these two state? Ice, in ice, the molecules, and the molecules in the water. In the water, the molecules are more randomly than the ice. Therefore, the disorder of the molecules in water is more than the ice. Therefore, the disorderness in water is higher than the ice. Entropy. So entropy is very important. And moreover, steam. You can also take the steam. The disorderness or randomness of molecules is much higher in steam than the water and ice. And the disorderness or the randomness, the quantitative measure of the disorder in a system is known as entropy. The quantitative measure of disorder in a system is known as entropy. So we can write entropy, the change in entropy. The change in entropy means suppose from ice to water or water to steam, the disorderness is changed. Therefore, the disorderness changes means entropy is changing. Disorder means entropy. So disorder increased or decreased, then entropy also increase or decrease. So the change in entropy, this is change in entropy equal to del Q by del T. Del Q means change in heat energy. Change in heat energy. And you can write the temperature only T. Change in heat energy, del Q means change in heat energy, and T is the temperature. Suppose if we can also write this one, ds and dq. This is a small amount of change. This is also a small amount of heat energy that changed. Suppose T1 to T2. Suppose T1 means suppose ice temperature, and T2 means water or steam temperature. So there are two temperatures. Now T1, T2, dq means change in heat energy, and heat energy means mass into a specific heat into temperature change. Heat energy means mass into a specific heat and temperature, change in temperature. Now you can integrate del T. Uh, and you will get S equal to, if you integrate del T by T, you will get ms T1 to T2 del T by T equal to ms mass and specific heat and ln T T1 to T2. Now ds equal to ms ln T2 minus ln T1. And finally ms ln T2 by T1 ds. This is the quantitative measurement of change in entropy. Quantitative measurement, change in entropy. This equation. We need this equation to solve a problem. Now, problem 3. Problem 3 said calculate the total increase in entropy when 1 gram of ice at minus 10 degrees Celsius is converted into steam at 100 degrees Celsius. A specific heat of ice and water is 0.5 and 1 respectively, and latent heat of ice and steam is 80 calorie per gram and 540 calorie per gram respectively. Therefore, we have to calculate the total increase in entropy of 1 gram of ice. Therefore, mass is given 1 gram. Mass is given 1 gram and ice first step, second step, third step, and we have to use this equation, and fourth state. First state, minus 10 degrees Celsius to 0 degrees Celsius, ice. Minus 10 degree ice, 0 degrees Celsius also ice. Question asked minus 10 degrees Celsius to 100 degrees Celsius steam. Therefore, minus 10 to 0 degrees Celsius and 0 degrees Celsius to 0 degrees Celsius water. This is ice, but this is water. And 0 degrees Celsius to 100 degrees Celsius water. Both temperature for water, 0 degrees Celsius water and 100 degrees Celsius water. Now 100 degrees Celsius water to 100 degrees Celsius steam. So first, minus 10 degrees Celsius to 0 degrees Celsius ice. The change in entropy for minus 10 degrees Celsius to 0 degrees Celsius, the change in entropy ds equal to m as ln T2 by T1, where T1 minus 10 degrees Celsius, this is T1. T1 equal to 10 degrees Celsius, 10 degree plus 273. Minus 10 plus 273. Therefore, it will be 263 Kelvin. Minus 10 and 273 plus 273, just degree Celsius to Kelvin scale. Now T2, this is 0 degree Celsius, 0 degree Celsius, this is T2. T2 means 273. 0 degree Celsius means 273 Kelvin. 273 Kelvin. Now mass is 1 gram and mass is 1 gram into 0.5. The specific heat of ice, the specific heat of ice is given 0.5. A specific heat of ice 0.5 and ln 273 by 263, 273 by 263. Therefore, the result will be 0.01865, 1865 calorie per Kelvin. Now for 0 degree Celsius to 0 degree Celsius, 0 degree Celsius ice to 0 degree Celsius water, and the equation will be for change in entropy equal to m SL by T. Mass is given 1 gram and SL means latent heat. There is no temperature change, no temperature change, then instead of specific heat it will be latent heat, latent heat. Mass 1 gram into 80, latent heat of ice, latent heat of ice is given 80 calorie per gram, and temperature 0 degree Celsius, 0 degree Celsius means 370 Kelvin. Okay, this is equal to 0.293, 0.293. Similarly, now for 0 degree Celsius to 100 degrees Celsius water, 100 degrees Celsius water. Similarly, the equation should be the change in entropy m as ln T2 by T1. Put this value, put the values, and you will get the answer for this changing is 0.312. And also for 100 degrees Celsius to 100 degrees Celsius steam, this is mSL by T, mass 1 gram, into latent heat for steam. Latent heat for steam is given 540 calorie per gram per calorie, and this will be 373. 100 degrees Celsius, 100 degrees Celsius means 373. 273 plus 100, 373, and the answer will be 1.448. And all of these three result, you have to sum, or total increase in entropy will be all of these three result. Just adding the 4 results, then you will get the final result will be 2.0707165 calorie per Kelvin. This will be the answer. Okay, next we will discuss about the Maxwell's thermodynamic relations. Maxwell's thermodynamic relations. Okay, to get the Maxwell's thermodynamic relation, we have to first know about the first law and the entropy, the equation of change in entropy. The first equation, the first thermodynamic, the first law of thermodynamics, we know dq equal to du plus dw. Change in heat energy equal to change in internal energy and plus work done, du plus dw. Now you know dq equal to du plus pdv, pressure and change in volume. Pressure and change in volume. Work done equal to pressure into change in volume. You know work done equal to force into change in distance, or the change in volume. The change in, suppose dl is the change in displacement. Force into distance, like that. And force equal to pressure into area, small area, dA, small area, and change in a small length, small distance. Pressure, force equal to pressure into area. You know pressure equal to force by area, just small area dA, force equal to P into dA, P dA dl. So area into length, this is change in volume, this is volume. Area into length, volume. So dW equal to PdV. And the change in entropy, ds equal to, we know, dq by t. So dq equal to ds into t, or t ds. So here du equal to dq minus pdv. This is equation number 1, and put this value here. You will get from equation du equal to dq means ds t ds t ds minus p dv. This is very important equation. Du, the change in internal energy, T, the temperature in Kelvin, temperature, ds change in entropy, P pressure, dV means change in volume. So we will get 5 parameters from this equation, that is U, first parameter U, T, second parameter S, entropy, S, third parameter, and P pressure, fourth parameter, and V volume, fifth parameter. There are 5 state functions. Parameters means state functions, U, T, S, P and V. These are the 5 parameters, and any two of these, say pressure P and temperature T, can be used to determine the thermodynamic state of the system. That means any two of these 5 parameters, 5 state functions, if you know any two state functions, suppose pressure and temperature, then you can determine the thermodynamic state of the system. Thermodynamic state of the system. At a systemer thermodynamic state we can find out. Suppose we know two state function P and pressure and temperature. We know these two state functions, P, pressure and temperature. We know these two state functions. Then the other state functions, suppose U, S and P, not P, V. From this equation there are 5 state functions. We know 2 state functions, and these are the other state functions we don't know. Now U is a function of P and T, and S is a function of P and T, and V is a function of P and T. If if you write x and y, then this will be x and y, x, y, x, y, x, y. Just pt. Xy means if we know p and u, or s and u, any two of the 5 state functions, any two means x and y. Then we can write x and y, x and y, x and y. Okay. If we write x and y in the state of p and t, x and y, any two state functions, and partially differentiate this equation, we will get du equal to del u by del x y dx plus del u by del y x dy. This is partial differentiation. then we will get du summon this one. And similarly for